Welcome everyone to our March session of GLOW. We're very excited for today. I'm very happy to introduce Petar Veličković, a senior staff research scientist at DeepMind and an affiliated lecturer at Cambridge. And today we're going to have a very exciting lecture on LLMs as graph neural networks, specifically to use tools from graph learning to study how LLMs can generalize. And I think that's very exciting and also ties with our discussion session last month, where we had sort of touched on this topic a little bit. So this is, I think, perfect timing. I'm just going to briefly introduce to you the format for today. So Petar is going to hold his lecture. There's going to be preset breaks in the middle for questions. The way we're going to handle this is that you can ask questions in the chat, and Max will ask some questions during the lecture. Perhaps you can maybe do upvotes or something so we can track which questions are the most interesting. And then after the lecture is done, we're going to stop the recording, and then we're going to have a 30-minute Q&A session with everyone. And so if your question hasn't been answered by then, you can ask it in the discussion session. All right. So without further ado, I would like to ask Petar to start his lecture, and hope you all have fun.
Wonderful. All right. First of all, I'd like to thank you all so much for coming to my virtual talk today. And also, I'm very grateful to all of the organizers of GLOW for giving me the opportunity to use this seminar as the first place where I will kind of release this content I've been creating to a more broader audience. As some of you know, I've given this as a lecture to my Cambridge students as part of our master's course in geometric deep learning. But because of various constraints, I wasn't actually able to release the recording. And also, I felt the timing was pretty good because I knew that in the GLOW community, there was a very nice discussion on, the future of graph learning. And I feel like this talk could be a good piece of that puzzle because what we're going to talk about today really is how you can take the kind of, I would say, typical knowledge that you learn as part of becoming an expert in graph representation learning and basically apply it to hunt for, at this stage, I would say, extremely low-hanging fruits in how modern language models are basically not working as intended, especially when generalizing outside of the distribution that they've been trained on. We'll discuss why this is an important and practical problem as well. And also, we will see that the reason why we're able to do these things so easily is because under the hood, large language models are really yet another instance of a graph representation learning model, one that, as we will see, uses a particularly unfortunate graph. So, okay, without further ado, I'm just going to start with a brief recap. I'm expecting that most of the attendees of this talk will already have a reasonable level of understanding of GNNs, but because there could also be people for whom GNNs are a completely new concept, I will just quickly introduce some of the key things, also to make it clear what kind of notation I will be using. So essentially, a graph neural network is any model where the input is graph structured. So you have a collection of nodes and edges connecting them. Inside the nodes, you have these node feature vectors, X. And what a single layer of a graph neural network does is it looks at the features of a node and the features of all of its immediate neighbors. And then based on the features in that entire multiset, it updates the representation into some latent space H. And this is then applied in a parallel manner in every single neighborhood inside the graph. And the way you actually implement that local function varies depending on the level of expressive power you want to have. But general purpose strategies can be classified roughly into three general directions. You have convolutional GNNs, attentional GNNs, and message passing GNNs. As you go left to right, here you can see their various equations. The expressive power of the model is increased. However, the model will then also have more parameters and be more prone to overfitting and harder to explain, harder to scale. So it's a trade-off you have to strike. And the attentional models tend to live in this sort of middle where you're learning only a coefficient of interaction between different items in your neighborhood, but otherwise you're still just computing effectively a weighted sum of all of your neighbors. And this is something that offers it nice trade-offs between expressivity and scalability. And we will discuss later on transformers very nicely fit in this middle ground of this picture. But yeah, the general components you need to keep in mind are we have this message function psi, which looks at the features of a neighbor and computes the vector to be sent across that particular edge. Then you have this aggregation function O plus. This is anything like summing, averaging, maximizing, anything which is permutation symmetric, so it doesn't depend on the order of the operands. That combines all of the messages into one. And finally, once you've done that, you can pass the resulting message in a update function phi, which might also have this neat little skip connection. So you update the features of node U based on its old features and based on the features of coming in from the neighborhood. Okay, so this is the general purpose formula. It typically leaves the graph alone. So it assumes that the graph you're given is perfect, and you're just learning the psi and the phi functions, which are the main parametric functions of your model. But actually, and this has been a topic that's been raging in the GNN community for many years, and I would argue now we pretty much have all converged to the understanding that this is not the right way of looking at things, because very often that input graph is not good for one reason or another. And here I've just given 3 different reasons with a few paper citations to indicate why that is. So first of all, let's assume for the sake of the argument that you have a perfect graph, which perfectly represents the problem you're trying to solve. Sometimes that perfect graph might just be really bad for solving the actual problem with a GNN. So for example, if your aim is to check whether pairs of nodes in a graph are connected, a problem I've investigated in our NeurIPS paper in 2020, the PGN paper, you can very easily come up with these adversarial path graphs where your GNN needs linearly many steps before these 2 nodes will talk to each other, and you will know that they are connected. But if you choose to represent your edges in a different way, using these disjoint set union find data structures, you can actually reduce the number of steps required to something which is basically amortized constant. In reality, it's the inverse Ackermann function, which is more or less constant for all the inputs you might care about. So even when the input graph perfectly represents your problem, it might be a really bad graph for the problem you're trying to solve, because the GNN needs many steps to reach a decisive answer. Then sometimes, even if you have good graphs, they might not be perfect graphs in the real world. We often use molecules as a standard example of a perfect graph, but in reality, it's just chemistry, and chemistry is an approximation for the underlying physics. And perhaps the most obvious example of this you see in protein folding, where proteins effectively, when you look at their molecular structure, are linear molecules. They're polypeptide sequences where effectively you have a chain of residues connected to each other. But what happens is this chain folds on itself in 3-dimensional space, and suddenly things that were really far away in the molecular graph become really close to each other in 3-dimensional space, meaning that the molecular graph has very long-range interactions that are super important, and doing just message passing over that input graph might not be the best way of dealing with that problem. And lastly, some graphs are just pathologically bad in the sense that you might not even be able to get good training performance when you use graphs like this. And the canonical example is this barbell graph where you have 2 cliques connected by a single edge. And this single edge, the bottleneck, is under a lot of representational pressure. As the sizes of the cliques grow, if you really care about every node in the first clique communicating well with every node in the second clique, you can hopefully see how that one edge is under a lot of pressure. And in fact, you can prove that as the sizes of the clique grows, the required embedding space on that one edge's message function needs to be exponential in the size of the clique. So for all intents and purposes, it's a practical impossibility result. You can't build a GNN like that practically, right? So there is an aspect of we do message passing over the graphs, but we need to be careful how we choose our graphs. Then another standard result, which I believe will be familiar to many of the people in this call, is that we can look at transformers as a special case of graph neural networks, because the way in which they are computing their answers is really by looking at pairwise interactions of words. So it's not a linear kind of sequential model word by word. Actually, every step of the way it looks at pairwise interactions between words. And basically, this is a connection that's been very deeply explored in previous works. I don't have enough time in this particular talk to get into the depth of this, but Chaitanya Joshi wrote this really nice blog post in The Gradient titled Transformers or Graph Neural Networks, which you can read, and it has a nice kind of in-depth analysis of individual steps of how the transformer lines up with the GNN. So if we kind of concluded that certain graphs are just pathologically bad, then it might be good to try to measure what makes a graph good. And this is something that there have been some very interesting developments towards in recent years. This might also be familiar to those of you who do research in graph rewiring. But basically, we have realized that if you want a graph which is nicely sparse, which has no bottlenecks, and so on, typically when you combine all of those properties together, you end up with a actually very well-defined mathematical structure known as the expander graph. And we have studied expander graphs as propagation templates in our own work, which was published at Log a couple of years back, and concurrently by Hamed Shirzad and his co-authors at ICML 2023. So expander graphs are basically, you should just think of them as a particularly good structure without any priors about what the input problem is about. It's just there to make communication between pairs of nodes as good as possible. But sometime after that, in work together with Francesco Di Giovanni, Konstantin Rush, and others that we published at TMLR, we actually found a formula for over-squashing quantification, which, as far as I know, for the first time quantifies to what extent will two nodes be enabled to mix their features as a function of the number of layers, so the architecture of the GraphNet, the norm of the weights, so the parameters of the model, and many different expressions of its adjacency matrix, i.e. its graph topology. Okay. So this was just a little bit of a recap of like all the different building blocks that are going to come together for our analysis of LLMs. But now we're going to dive headfirst into LLMs, which is really going to be the meat of this talk and where we're going to spend most of our time. So surely most of you are well familiar with LLMs by now. So why should we give yet another talk explaining how they work from different perspectives? Well, I must stress that our motivation here is not a theoretical one. It is actually a practical one. And I'm going to start by telling you about the practical problem. So specifically, you've all witnessed the direction in which large language model systems are going these days. Generally, there's a lot more emphasis on deploying them over super long executions, right? So you have now state-of-the-art models like Gemini, now 2.5, which support context windows of millions of tokens by default. So now you can already do language tasks with 1 million or 2 million tokens. And there are practical systems you can use that offer you this capability. Then you have the great recent resurgence of long chain of thought models through these so-called reasoning LLMs. They typically answer questions that you ask them through very long sequences of steps. So there's a lot of tokens that are generated as part of answering every particular question, especially if these are hard questions. And there's also a general shift towards agentic systems, such as the various incarnations of deep research, first released by Google, and then afterwards by OpenAI and XAI. These systems basically break a problem down into many different subtasks, and then they try to answer those subtasks separately, perhaps by invoking tools and kind of incorporating all these answers and orchestrating all of these components together. So these are all very challenging tasks requiring a really long trace of coherent state. And if you fail on any particular subproblem, either in your reasoning trace or in your agentic problem, it might mean very easily that you fail on any downstream application that you're trying to deploy this in. So I would argue it's critical that when you build a system like this, it should try to remain robust as you increase the execution lengths. And arguably, we're only going to be running these models on harder and harder problems. So long execution lengths are really here to stay, and they're only going to get longer as we progress. However, robustness is not really there. And what do I mean by robustness is not really there? I need to express that there's like basically a very interesting dichotomy currently in transformer-based models, where on one side, they're capable of truly impressive things sometimes. So you might be familiar with the AlphaProof system, which is a large language model-based system that was able to win a silver medal at last year's IMO. And also, obviously, the AlphaFold system, which is now based on transformers, which was an important component in last year's Nobel Prize in Chemistry. So certainly, transformer-based models are taking part in scientific discoveries that are recognized as highly relevant. However, at the same time, you ask them to do something, not complicated research-wise at all, arguably something that they should be well-positioned to do. For example, you ask them to multiply two numbers, right? So LLMs, they, as you probably know, have often hundreds of billions of parameters, and those hundreds of billions of parameters are often spent on multiplications, right? So there's lots of multiplications happening inside this model. So it's well aligned with what the model is doing. Yet, even though they spend hundreds of billions of operations per single output unit, they cannot really reliably even perform those basic operations. And here you have, just as an example of an earlier reasoning model, O1 Mini. This was a snap I got from Twitter, basically showing how as you increase the number of digits of the two operands, the model starts to collapse and gets iteratively worse at predicting the outcome of multiplication, even though it surely has more than enough multiplications in its firepower to be able to fit such tasks. So this is a very interesting dichotomy, and basically kind of illustrates some cracks in the system, which we have to get better at understanding and patching as we deploy these models on ever longer tasks, right? So you might get really good performance on like individual problems with very concentrated chain of thought. But if you ever want to orchestrate an entire project, you're going to need to think about these kinds of robustness problems, because they will creep in as problem size grows. This is, we will discuss this. This is basically unavoidable in the way the systems are built right now. And, this is a very interesting question to just carefully ponder, right? So we want to be able to understand why there's this discrepancy in robustness, and also to find some ways to scalably solve the problem. And a very neat way to both mathematically formalize it and look at a practical problem is the task of length generalization. So we focus on that because out of all possible distribution shifts, it's arguably the easiest one to measure at test time. And arguably the paper from Anil and others that was published at NeurIPS 2022 was one of the first ones to kind of introduce and make popular the term length generalization, where they define it as the ability to extrapolate from short problem instances that the model might have been trained on to longer ones, right? And one very typical property of length generalization is that outside of the training set, so here we have two specific tasks studied in that paper, like parity and variable assignment, you get really good performance in the training regime. These are the lengths highlighted in the shaded region. But then as you ask the model to extrapolate to bigger problem sizes, you typically observe quick collapse. And another thing which is really important is that this collapse does not get any better as you scale up the model. So every curve that you see in this plot is a different level of scale, from 200 million parameter models to 64 billion parameter models. And you can see the performance doesn't really improve when you change the scale. In fact, sometimes it might even get worse. So basically, this is one of the reasons why this is a tricky problem, because you can't easily solve it just by throwing more compute at the problem. And arguably, this is something where we can use geometry and graphs to meaningfully make a dent. These kinds of problems, arguably, for several years now have puzzled LLM researchers. But as we will discuss today, they can be quite obvious sometimes through the lens of geometric deep learning or graph machine learning. And that is because LLMs are, by their design, vulnerable to length generalization from a variety of perspectives that are, I would say, purely geometric. Like the choices of how you model them from a graph topology perspective, for example, very easily correlate to the failures that they're going to make. And in the previous blocks that we've discussed, we've already covered most of those perspectives that we're going to need. So let's try, to be the lonely wizard that has this knowledge of graphs and geometry and maybe topology, and try to scale this mountain of LLMs. As mentioned, it's the first time I'm going to be giving this talk broadly, so any and all feedback throughout the talk afterwards, you can reach out to me via email afterwards, is super, super welcome. So let's see what we can do. Before we dive in, I'm sure you've seen 100 of illustrations of LLMs before. I'm just going to give you one more so that you can hopefully maybe even get some perspective of it, which is a bit more graphy than what you've seen before, and also so that you're very clear on what kind of representations and assumptions I'll be making about how the model works. Hopefully you'll agree with me. The assumptions are fairly generic and they won't be too limiting, like they'll be able to allow us to talk about basically all the modern GPT or BERT style models. Okay, so let's assume the way typically modern LLMs are running is as next token predictors. So you have a string like a house of, and you want to continue that to be a house of cards, for example. The way typically the LLM will continue to process this sequence is you will first chunk up your text into pieces, these chunks known as tokens. They're sometimes corresponding to words, but not always. I think in this case, I checked with the Gemini tokenizer. It literally tokenizes the 3 words separately, so it's exactly like this in the LLM. You then use these token identities to index into a lookup table. So you basically learn a separate real-valued representation of each one of these tokens. And then what you do is you alternate 2 different types of layers. The first type of layer is a feed-forward network. This is your typical local permutation equivariant layer applied to every single item separately. So this can be just, for example, a 2-layer MLP. So here you have these weights and biases, which are the learnable parameters, and you have some activation function like well, in modern days, it will be something like GelU or GEGLU or Swish or something like this. Okay, so one type of layer just takes the embeddings of each token and updates it to some different latent space. And the second type of layer is the attention layer. So in this particular layer, what we do is we allow words to interact with each other. So effectively, you compute the representation, for example, of the token of by computing a weighted average of the embeddings of all of the other tokens in a way that you first compute a coefficient of interaction between these 2 words by basically computing a query vector for of and doing a dot product of it with a learned key vector for the corresponding word. Then you pipe all of these coefficients into a softmax function, so you get nice coefficients that sum up to 1. And these coefficients are then multiplied with an appropriately derived value vector. An interesting question that might be asked then is, why do we not allow backwards connections? So why do we not allow the vector for house, for example, to send its embeddings to the vector of A? And the reason for that is that we're basically training these models in real time to be next token predictors. So the vector for A is then tasked to predict house, and you get a loss function there. The vector for house is asked to predict of, and the vector for of is asked to predict cards. So if you allow the backwards edge, if you allowed the vector for house to send its embedding backwards, you would effectively allow the model to cheat. And it would be trivial to predict house from A in that case. So in order to be able to train at scale, at huge quantities of text at the same time, you basically only allow this attention mechanism to act on the words preceding the given token. Okay, so the graph enthusiasts among you will have probably noticed that there is something that looks very graphy in this architecture. And indeed, we will be looking very closely at this particular graph. And as I hinted to you at the beginning, this choice of what we call a causal mask is actually a really bad choice of graph, especially if you want to generalize to bigger problem sizes. But we'll get to that. We'll get to that in a bit. So this is zoomed out. To make it more clear what are the different places where we can apply our graph or geometry knowledge to improve the LLM, I'll also give you a version of this picture in a more zoomed in manner. So let's imagine, we have 3 token embeddings. How does a single transformer block transform this data? First of all, in order to be able to do the attention mechanism, we compute a query, a key, and the value vector separately for each one of these items with a learned transformation matrix for the query, the key, and the value. Once we have those, the queries and the keys are jointly combined to compute the attention logit, which is the unnormalized coefficient of interaction between the two items. And the way it works is essentially you compute a dot product between a particular query and the corresponding key that it's attending over. And this gives you the amount of significance that the network gives to token V towards token U. One key difference, which often takes place in modern LLMs, is that you further rotate these vectors prior to taking the dot product by applying this rotary position embedding, or ROPE for short. In short, there is some kind of a rotation matrix that is applied to these two vectors before taking their dot product, and the exact amount by which you rotate, so the power of this matrix, is dependent on the distance between the two tokens. So that's why you have the U minus V in this power expression. Once you have the logits, you need to softmax normalize them. And also, as we discussed, you need to disallow tokens in the future from sending information into the past. So you have this basically a bias matrix, which just masks out the entries that we don't want by basically adding a negative infinity logit to each one of them, so that when you pass these through the softmax function, those will basically become zeros, right? And now we have nice normalized coefficients, which are going to be effectively this lower triangular matrix, and in every row they're going to sum up to 1. So once you've done that, now those softmax coefficients tell you exactly how to recombine the value vectors in order to get the embedding of each individual item after the attention layer. And usually there will be a residual connection applied to this too. So the actual final embedding you'll get here is the embedding at the input level plus the weighted sum using the attention coefficients of the value vectors. And once you have those, then you can do the second stage of applying your feed-forward network, potentially with some layer or RMS normalization and another skip connection for good measure. So up to first approximation, this is not necessarily everything that's going on in a modern LLM, but up to first approximation, it's most of the things that are going on in the modern LLM. And if you think a little bit, I think it shouldn't be too hard to identify some of the key parts of the GNN equation inside what I just drawn for you on this slide. So here I'm kind of explicitly calling it out. Of course, you'll have the recording later on, so you can focus on this a little bit more. But essentially, the attention mechanism supports an attentional function in an attentional GNN. The neighborhoods that you have for your graph aggregation are given to you by this bias matrix. So the entries which are not minus infinity tell you the allowed neighbors in your graph. And your aggregation function after you run the softmax is just summing. And the feed-forward network actually very nicely corresponds to the update function in GNN. So there's actually a pretty neat correspondence between every chunk of the GNN equation and what's happening inside this particular transformer block. Okay. So hopefully this makes sense. From what I've seen in the chat, there haven't been any questions. So I'm hopeful that what I've presented so far has been reasonably okay. Now we're finally going to investigate some interesting failure modes of models built in this way by studying their graph. And actually, I'm going to start with a somewhat interactive question for the audience. Now, I will ask those of you who have read the corresponding paper to not answer this question because I want an unbiased sample, okay? So we're going to start by asking the model to do something that arguably you need to do quite often in agentic tasks, right? Because if you want an LLM to execute many things without human supervision, it often needs to execute code to find the answer to some question. And then you need to be able to copy that answer into something else, right? So that you can chain the different invocations together without human supervision. So copying is arguably a super important thing for LLMs to do, okay? And they need to be able to do it well. So let's start by asking the model not to copy everything, but just to copy one digit. in a collection of digits. So a much simpler version of the more general copy task, right? And we started out by asking Frontier LLMs two different questions. The first one is, what is the last digit of a sequence of ones followed by a 0? And the second one is, what is the first digit of a 0 followed by a sequence of ones? Now, of course, the answer to both of these questions is 0. But one of them, and as you might expect, LLMs eventually will not be able to answer this question meaningfully. They will just say 1 rather than 0. But it's interesting to ponder which one of these two is harder for the LLM. Okay, so the way we're going to do this is I'm just going to ask you to write in the chat just a quick message if you agree. So if you think that predicting the last digit is easier for the model, please write something in the chat now. So who thinks that predicting the last digit should be easier for LLMs than predicting the first digit? Okay. And actually, yeah, so lots of comments pouring in. Last. Okay. So comparatively, if you think that the first digit should be easier, please write first in the chat. I'm going to give you a little bit of time. And once again, do not answer this question if you've already seen the paper. Okay. This is actually a very different distribution. Well, I would say it's about 50-50 from what I've observed. But it's a very different distribution to what I observed when I taught this at Cambridge, where there were maybe 3 or 4 people saying first and almost everybody else said last, right? So as you might expect, now I can spoil the big surprise. It's actually the last digit prediction, which is harder than the first, okay? So obviously, past a certain length, the models are going to fail, but they're going to fail much sooner at predicting the last digit than predicting the first digit. And I think one reason why a lot of people's priors are that the last digit will fail first, that the first digit will fail first, is because we try to anthropomorphize these models to some extent. Like we think what would be easy for us as humans, right? So for us, obviously, predicting the last thing you heard is much easier than predicting the first thing you heard, especially if there's a lot of things in between, right? But actually, LLMs are not humans. They do not fail in the same way as humans. And actually, humans probably don't have the same computation graph as LLMs do, right? So let's study graphs a little bit in light of this. And, I would argue it's quite counterintuitive at first sight that the model will fail on the last digit prompt much sooner than on the first. So the reason why this happens is because of the autoregressive nature of the computation graph, and specifically because all the paths that matter for next token prediction, as we looked at a previous visualization, they must cross in the last layer embeddings of the final token. So here we have a 5-token system, and initially we feed this through a bunch of transformer blocks, and this shows you how data is allowed to flow between the different embeddings in a 3-layer transformer. And it's the 3rd layer embeddings of token 5 that are actually used to predict the answer or whatever comes next, right? So all that matters for the prediction must cross in this particular embedding. And this is the problem, right? Because this is effectively a bottleneck. We talked briefly at the beginning. Bottlenecks are not a good idea. And essentially, we can use this bottleneck argument to construct a family of inputs. And this is a theorem that we have been able to prove that, you can just gradually increase the size of the problem. And that's what we do in length generalization. We study what happens as the problem size increases. And we can make a family of inputs where the change in the final token embedding becomes smaller and smaller as you go through the family. And eventually, it becomes smaller than any epsilon that you want, right? And this is what this looks like pictorially. So one typical example you can build is a bunch of ones followed by a 0. This is an example we looked at. And the embedding of that last 0 gets actually closer and closer and closer together as you go through this family. And in the infinity norm, we can take it below any epsilon we want. We just need a sufficiently large number of ones. Okay? And I hope you can now see why this can be a reason why models might not perform so well when length generalizing, because if I give you a problem size that's big enough for this epsilon to go below your machine epsilon, which is the smallest number that your computer can represent. Once again, refresher on numerics, computers cannot represent all real numbers. Computers can only represent a very specific subset of rational numbers specified by the floating point protocol that they're using. And machine epsilon is the smallest such representable number. The moment this epsilon drops below that, your model has no way of distinguishing two different sequences and must answer in similar ways when given those two inputs, right? And I must stress also that in modern artificial intelligence systems, if you've taken a numerical methods class before, you might know that, okay, machine epsilon is actually not so big, so it's not so bad. But modern AI systems are trained no more than 16-bit floating point numbers. But then in practice, when you serve them to make the inference very efficient, you will not only use smaller precision, like 8 bits, but you'll also quantize them often. And quantization even further chops off the set of representable numbers that this protocol can handle. And as a result, this machine epsilon is actually in practice way bigger than what you'd expect. And as a result, these models break way sooner than what our theory predicts they were going to break. And you can observe this in models that allow you to inspect their internals. So you can see the plot on the right, which is the representation of the representation difference in a task of just counting ones from a sequence of a bunch of ones. And this is in one of the Gemma family models, so we can inspect the actual embedding distance as you increase the number of ones. And you can see very quickly, already when you reach 11 ones or 50 ones, the difference between two successive sequences in the last token embedding in the infinity norm are actually pretty much at the level of the bfloat 16 precision, which is the dashed line. So you don't really need to amplify these inputs too much for this particular problem. I see there's a great question about the in degree of the last digit's attention. Yes, exactly. Hold on tight. We will talk about this in one of the subsequent papers. So one thing that's important to note is that these problems don't just make copying a single digit hard, they also make counting very hard. And when you ask transformers to do various kinds of counting, like summing up a bunch of ones or counting ones in a bit string or counting words in a sentence, whether or not you include chain of thought or anything, as you increase the sequence length, the errors increase. So on this particular plot, the blue bars are errors. So the bigger the bars, the worse it is. Now you might see these plots and think, oh, wait, maybe that's not so bad because, okay, the errors seem to be predictably increasing. So maybe the model is at least doing something smart and just gets less and less accurate over time. But then you plot the actual numbers that the model predicts and you see that the model is actually not doing any robust thinking whatsoever. In fact, it most commonly, when it sees a bunch of ones that you need to sum up, it just says the answer is 100. So you see here the histogram of all the outputs of LLMs on these inputs. It just says, I'm not going to bother trying to actually do the calculation. The answer is 100, right? So it's basically another issue where these representational collapse just makes it hard for you to do meaningful counting in these models. Now, okay, so this explains to you why the collapse has happened in the first place, but it might be interesting to ponder again, why did this counterintuitive result happen? So why was the first digit so much easier to perform on than the last digit when you'd expect, the model has a strong bias towards very recent digits, right? So as just when it's trained on the English language, the last few tokens are the most meaningful ones usually. So looking at the computation graph, can anybody guess why the first token is much easier than the last one? Anybody? You can write your thoughts in the chat if you'd like to. Right, exactly. So the first digit is included in the intermediate representation of all others. And I'm just going to ask LaTeX to help me with this, right? So I've picked an early token in blue and a late token in red. And I've asked LaTeX, draw me with light blue a path from the early token to the sink, and draw me with light red a path from a late token to the sink. And you can see very easily, just topologically speaking, the early tokens are at such an unfair disadvantage, right? Unfair advantage, that basically they will overwhelm the late tokens as the model gets deeper and deeper. There are actually exponentially many paths that early tokens will have access to spread their information. Whereas, for the last token, it's particularly bad because there's exactly one path in which it can preserve its information, right? And if that path fails, no matter how much the model tries to protect it, especially as you link generalize, you're going to have a bad time, right? And we can actually prove this, and we use a very similar over-squashing analysis that you'd observe in over-squashing papers in GNNs. Like, we study the gradient that the final prediction has with respect to a particular token's input embeddings, and we can easily find that there is a nice correlation to the number of paths that token has to the sink, right? And actually, then you can use this to prove an even more obnoxious result, that if you were to build an infinity layer transformer in the limit, the first token is the only token that the model will be able to represent, because the first token will exponentially overwhelm everything else, right? So this is also something that you can easily prove by just studying the topology of the graph. So, okay, this is the first kind of results that we can see that, the choice of the topology is a good indicator, first of all, that certain tokens are unfairly treated compared to others. And then also that there is a collapse that happens because there's a bottleneck through the last token. And obviously, the more inputs you have, the more things you're compressing through this bottleneck. This is an argument which, arguably, when you look at it as a graph problem, it becomes quite obvious, I would say, especially if you've studied things like over-squashing or graph rewiring before. Okay, but of course, you could say that all of these problems would be surmounted if you had a super sharp softmax that picks out, exactly the right attention coefficients to save that last token as much as possible, and, sparsify the graph, do graph rewiring in a way that it becomes more favorable, right? Now, the question is, are modern LLMs actually capable of having sharp softmax? Here we define a function to be sharp if the output depends on a constant number of inputs, right? So are you able to predict things like max, which, by the way, softmax is designed to approximate argmax, right? So one thing that you might be led to believe if you look at related literature of transformers is that actually, yes, softmax is indeed capable of saving the graph. Here I've restated the general softmax function and how it's computed given a vector of logits. And it's generally assumed because in a lot of these papers, starting from the earliest transformer paper, actually from Waswani and others, you have these very nice visualizations where they explain the behavior of the transformer through this sharp subgraph, which the attention is learning, right? So here for a translation task, but many years later, you now have this whole subfield of mechanistic interpretability, which tries to detect circuits inside the attention. And this paper from Olsen and others has these really cute visualizations where basically, only a handful of the coefficients are kind of sharply attending. And that's kind of a mechanism by which the model's doing its robust reasoning, right? So when you see papers like this, you'd be led to believe that this is how the model works. And indeed, it will work like this no matter how big of a problem you throw at them, right? Well, we actually prove that that's impossible. So we prove that the way we build transformers right now, there is no way in which they're ever going to be able to retain this sharp behavior as you go on, right? And this should hopefully relate to Petko's question in the chat. So even if you imagine you have, say, this 4-token input where the model has really learned to pick out the 4th item, has the highest logit, it's the most important one, right? I prove to you that no matter what the problem is, what the attention head is, as long as you're using softmax attention and dot products, I can add sufficiently many tokens, and these tokens can be garbage, just to be clear. They can be completely useless for the problem you're trying to solve. I can provably push this coefficient on the 4th item below any epsilon I want, okay? So as you increase n, essentially, and yes, exactly, in response to Petko's question, if you have an exponential number of weak paths, that is not insignificant, but all paths must become weak over time, is what this result is all about. So out of distribution, these coefficients will all collapse below any epsilon you want. And this is the full statement of the theorem. I'm obviously not going to go through the details of it. I'm just leaving it here in case afterwards you want to take a look and kind of inspect the various assumptions. But basically, we prove that these coefficients must decay below any epsilon for a sufficiently large problem size. And rather than showing you how this theorem is proved, I'm just going to show you what are the assumptions of the theorem afterwards. But first, I need to stress that this is not just a theoretical effect. This is an effect that you can very easily observe in attentional models that are both small and large, right? So let's look at finding a maximum of a list of items. This is the very problem that Softmax is designed to approximate, right? So I don't know if you can see my animation. I hope you can see my animation. This is just a single head set transformer, which basically, it's the most simple single step of attention aggregation to predict the maximum of a list of items. I've deliberately chosen this because you only have one attention head. So there is a clear correlation between what the head is doing and the predictive power of the model, right? And what I've done here is the rows of this matrix are just different inputs, so different random inputs in a batch. And the y-axis, the columns, are the attention coefficients on the 16 largest items in my list. So if the mechanism is working correctly, you would expect all the attention to concentrate on the far right column. That's the maximum item. Now what happens is every frame, I double the number of items, starting from the training set size, right? And you observe this very beautiful dispersion effect where basically all the coefficients decay towards uniform as you increase the number of items you're dealing with. And you can also observe this effect in large language models, for example, Gemma 2B, which I'm plotting here. The main difference is that in language models, you don't have this nice one-to-one correspondence between, what the attention head is doing and what the downstream task is, because there's a lot of heads and they interact in weird ways. But you can still measure the level of dispersion by quantifying things like the Shannon entropy of those heads. And as you can see, the entropy increases for all individual heads in Gemma 2B as you increase the number of items that you're trying to compute the maximum over, right? So this is an effect that's quite apparent and not just the theoretical result. I'm just going to highlight what are the 4 key assumptions of the theory. And this is where things become really cool, because you can use the results of this theory to propose improvements to the architecture later on, right? So the 4 key assumptions are: first, temperature is non-zero. Obviously, if temperature is 0, then it's just max and it's going to be sharp always, but you don't always want that. There is the assumption that each attention head fully attends over prior tokens, so that you have a fully connected causal graph, effectively. That your inputs come from a tokenized vocabulary. This is a very important assumption, very common in modern LLMs, but it's the very reason why you get this provable collapse. Because starting with a fixed set of tokens means you start in a compact space, and it's a known fact in real analysis that continuous functions take you from a compact space to another compact space, right? So there's always going to be a bound on the possible logits you can get, and this in turn bounds the coefficients you get as the output of a softmax, and they must decay with the number of items. And of course, you also have to assume that all of your layers are either continuous feed-forward networks or self-attention. Great question, Vinicius. Yes, this is exactly what local versus global layers are trying to address. We'll talk about this in the next segment, actually. So basically, this is the reason why those assumptions are important. So 0 temperature is pure sharpness, full attention ensures your neighborhoods grow with n, and fixed vocabulary ensures your inputs are on a discrete set of vectors. And then we just apply a standard fact in real analysis to prove that you cannot escape the cage of the logit values that pushes you back down as n grows. And this also hints at possible fixes like adaptive temperature, sparse attention, having LLMs without tokenizers, or even layers with discontinuities in them. But we'll focus on the sparse attention, which was exactly what was Vinish's question in the chat. So great foreshadowing. And this was a paper that very recently we put on the archive where Alex Vivitsky was the first author. So just to be clear, what did we find? We found that because of this over-squashing and bottlenecks, modern LLMs have really bad graphs from the perspective of over-squashing. And these graphs, as we know, when they're bad from the perspective of over-squashing, they need to be rewired. Now, attentional mechanisms can help you rewire up to a degree, but as you increase the problem size, as you try to generalize, they're not going to help you because of this dispersion effect. As n grows, the attention coefficients will go back to averaging, and you're back to the bad graph you started from. So I'm going to repeat it again, this time in all caps. We need to rewire these graphs, okay? This is really important if we want to generalize. And who better to do this than people who are GNN experts, right? So there's a few things that you can do to fix this autoregressive nature of the graph. We played a little bit with directly combining LLMs with kind of more standard bidirectional GNNs in our Transnar paper. I won't go deeper into the details here, but I've left it here as a reference if you'd like to examine that a bit more. However, these methods are somewhat unwieldy and they're not as easy to scale. So it will be easiest for scaling if we keep our graphs feed forward. So we only allow edges to go in the from past to the future and never backwards. And turns out this is actually quite hard. So most of the analyses that we know from undirected graphs no longer apply to this regime, right? And for example, there's no such thing as expanders anymore, or at least we don't know of anything similar to expanders in this feed-forward regime, okay? So let's ask the question, what makes a good feed-forward graph? So what makes a good directed graph without backwards edges? We've thought about this a fair bit, and we tried to distill the best things we know from how expanders are defined and kind of generalize it to the directed case. The only measure that we were sort of very easily and usefully able to generalize so far was this idea of mixing time. So one way to define a good expander, among other things, is that the mixing time of its corresponding Markov chain is very favorable and low. So basically information mixes quite quickly. In the case of directed graphs without back edges, obviously you don't have a stationary distribution like that. But assuming that you only have one final token, only one sync token, you do have a stationary final state where all of your values have converged to the final token, right? So you can measure how quickly the graph passes the information to that final token, right? How quickly does the data travel? So you can define this random walk matrix, just scale each edge by the out degree of the node. That's this delta V outwards. And you try to find, what's the smallest number of steps needed such that when you raise any input distribution to a corresponding power of the walk matrix, you approach this final stationary distribution with some probability or with some norm, which is less than a quarter, though a quarter is an arbitrary choice that you can make here. I think as long as it's less than a half, it will work. Another thing you can do, so mixing time tells you how quickly data travels, but as we discussed in the case of the over squashing and bottlenecks, it doesn't matter if the data travels quickly to the final token if it doesn't arrive in one piece, right? So basically, if you lose all the information in your late tokens at the expense of passing your early tokens with a lot of pads, you're not going to have a good time. So we also measure a converse process, which is fidelity. So how sharply does this data reach the final token? To do this, once again, we try to abstract away the effects of the attention. As we discussed, because of the softmax dispersion, it's going to get closer and closer to averaging anyway. So let's assume that we just do this diffusion process where now we scale by the in degree of the receiving node. We assume every node is just averaging everything that comes in. Note that unlike the out degree case, this no longer yields probability distributions when you raise it to powers, right? However, you can raise it to powers and check, this particular expression over here, the minimax expression, which quantifies what's the most sharpness you can salvage from this particular graph if it always averages. To clarify this formula, what you first do is you check, so you maximize over all powers of this matrix. You search for the number of steps at which a particular token is sharpest in the final token, that's tau. So the largest possible value that you get by raising this diffusion matrix to a given power. And then you look at the worst case token, right? So that's why there's a minimax in there. So you search for what is the token that has the least favorable propagation into the sink, and at arbitrary numbers of layers. Note that the maximizing number of layers is obviously different for different tokens. Here we're subtly assuming that there is a good residual connection which salvages your embeddings at every single layer to the extent that's meaningful. But this formula here basically measures the worst case scenario of how well information travels to your final token. And optimizing both of these things together, mixing time and fidelity, is quite hard. So keeping mixing time low and fidelity high, really tricky. And hopefully you can see this on the specific cases of, here, for example, we have fully connected graphs, which is like a standard kind of causal attention mask. The mixing time is logarithmic, so that's good. However, the fidelity is only 1 over n. You can never do better than just pure averaging of everything in a graph like this. So that's not so good. If you take the exact opposite of this, which is a line graph, that's the most local graph possible, also the graph used by LSTMs and similar models, you get not so good mixing time. It's now linear in the number of steps. But your fidelity is now much better. You can use Stirling's approximation to prove that now it's square root of n better than it was for the fully connected graph, right? So this information will now stay stable over much longer contexts, right? And this exactly answers the question that I think Vinicius asked in the chat. Local layers are good for fidelity, right? At the expense of mixing time. But optimizing them together is quite hard. And it's a discrete optimization problem. So we asked FunSearch, which is a methodology we've developed within Google DeepMind, to help us optimize this objective. What's cool about FunSearch is it's basically like a genetic algorithm, but it uses an LLM as a mutation function. So it generates code, right, which synthesizes these better mask matrices that optimize both mixing time and fidelity at the same time. And it discovered this pattern over here initially, which, we never thought to do something like this, but in retrospect, it's a pretty cool idea. And it was completely proposed by the system, right? You have these nice, basically bipartite graphs, right? So essentially, you cut your tokens into chunks, and you allow each chunk to move into the next chunk following this bipartite graph. And hopefully it's obvious to see why this might be a good idea. The bipartite edges allow you to quickly move across blocks, so you're going to have a good mixing time. But because you have much fewer incoming connections than in the full graph, you'll have better fidelity, right? And one key issue of this graph as it is that there's no self-similarity. And often in transformers, you need to predict not only in the last token, but also in all the intermediate ones. So this matrix will not be a good one if you want to predict anywhere in the middle. But we can fix that by basically adding recursively connections inside these triangles in a self-similar way, and also correspondingly sparsifying these bipartite edges. While there's no feed-forward expanders, there exist bipartite expanders, and we know how to build those quite well. So we sparsify these squares by using known procedures to build approximate bipartite expanders, and we arrive at what we call the FunSearch graph, which we can prove has mixing time polylog n, which is obviously much more favorable than linear, slightly worse than log n, but manageable. And fidelity, we don't yet have a proof for the form of the fidelity, but we found that it's really controllable. And you can control the fidelity by basically the degree to which you sparsify these squares. The more sparsified they are, the better fidelity you're going to get, right? And specifically, here is basically a scaling law of what kinds of fidelities you're going to get if you choose different numbers of connections in each one of these squares, right? So as you increase the number of connections, the point at which the problem size has a certain fidelity changes. But while we don't have a concrete proof yet, you can certainly use this to control what's the best graph for the level of fidelity you require. And I should stress across 3 tasks, some of which are very challenging for GNNs and transformers when they're doing this sequentially. So predicting maxima, predicting second maxima, and predicting parity. These graphs, the FunSearch graphs in red, are by far the best sparse graphs that we've been able to find, right? They are still not completely catching up to the fully connected graphs in green in all of these problems, but arguably that's because we've only been able to test them on relatively modest problem sizes, up to a couple thousand tokens. The dispersion effects really start to happen when you look at millions of tokens. So basically, it's at these scales where you would expect the full graphs to collapse. But as far as sparsity is concerned, this automatically discovered graph seems to be a much better candidate than basically taking things like Erdos-Renyi graphs or taking an expander graph and orienting it or anything like this. Okay, so there was also, quickly, I want to mention something about these rotary position embeddings before we conclude. Because it's not just the graphs. There's also many geometric properties that directly control how LLMs behave and also which graphs you get. And position embeddings that all modern LLMs use are usually the rotary position embeddings, or ROPE for short. And the way they work is you modulate the dot product between your logits using the positions of the respective tokens. And as such, it directly impacts what graph you're going to get as a function of positions. And the way it works is you define this sequence of rotation angles. You have this base wavelength theta, and then you raise it to different powers based on your embedding size. You chop your embedding into two-dimensional pieces, and at each two-dimensional piece, you rotate with a corresponding 2D rotation matrix, right? And then you just compute a dot product between query and key, where you've rotated every two-dimensional chunk of the query using this corresponding rotation depending on the distance. So your attention logits are then basically just your usual dot product between the query and key, but appropriately 2D rotated depending on the distance. And it's been long believed since the original rope paper that models use rope really well because it basically allows you to decay attention with distance, right? So as two tokens are further apart, the rope activations go smaller and smaller. We prove in our paper, first of all, it's a very simple geometric fact that this is not the case always. And in fact, we reproduce their result when queries and keys are constant vectors. But in a more realistic setting, like if they're Gaussians, there's actually zero dependence on distance. Like there's no decay with distance. You can maximize the embedding size, activation magnitude at any distance that you want. So to understand how rope is really used, we need to look at which frequency bands are most used. Remember, rope chops your embedding into 2D pieces, and we can check which of those 2D pieces are more favored in terms of norm by the LLM. And this is in Gemma 7b. We find that most of these attention heads actually prefer low frequency parts of rope, but there's a handful of heads that really like high frequencies. And all of the heads that like high frequencies look like this. We looked at them, basically. We inspected all the individual heads in Gemma 7b, and we found that whenever there's a high frequency dependence, the head is like this sharp diagonal or off diagonal attention. So there's some correlation between high frequencies usage and positionality, and we prove a theorem that shows how a rope can help attention heads do this positional attention. So you start basically by preparing a bunch of key vectors and query vectors, and the query vectors are appropriately rotated versions of the key vectors, such that when you do these 2D rotations, the key and the query line up perfectly in this high frequency at the right offset that you want. And then because of the pigeonhole Dirichlet principle, even though these other keys are going to rotate around the circle, because the length is 2 pi, and your multipliers are integers, you'll never get better alignment than what you got with the desired offset. So all you have to do then is amplify the norm, and the cosine will be less important, and you'll end up with these nice offset attention maps as a result. However, most other heads just use the lowest frequencies, and that's because you don't need to do positional stuff on those heads. That's because those heads spin the slowest and they cause lesser interference at those frequencies. So they're more suitable for semantic information exchange. But that being said, they still spin. So if you have a large enough problem size, you'll get the kinds of spins you've never seen at training time. And this will cause destructive interference. And we can prove there are certain problems you'll never be able to length generalize on under certain assumptions with rope. So since low frequencies are used to pass semantic information, and those frequencies are basically just distractions, could we just delete them? And this led to us proposing p-rope, which we'll be presenting at iClear in a couple of months. And the results are pretty wild. We're able to delete 25% of the lowest frequencies of rope, just set them to 0, nothing else required. And the perplexity not only doesn't get worse, but actually it's even competitive with the full-on rope, right? So some key takeaways I'd like to leave you with, and then we can dive into discussion. LLMs are GNNs. There's a very clear graph of tokens interacting with each other. And if you work with them, you will benefit from understanding them as graph-structured models and taking advantage of their geometry. And the graphs which modern frontier autoregressive LLMs use are highly suboptimal. And attentional mechanisms can help you rewire them to an extent, but not in a way that will generalize to ever-increasing sizes. So length generalization problems are inevitable as you scale context windows ever more and as you ask your model to behave more agentically, right? So now that we've ascertained how you can use the skill set that is typically kind of understood as one becomes an expert in graph machine learning, now hopefully you can use these newfound powers to make things better for LLMs and kind of contribute to how these systems will develop in the future. Because I would argue we are like the GNN community, we are the best positioned to make this change in a meaningful way. So I'll leave you with that and kind of leave you to go and try to scale your own LLM mountains using the sorcery skills that we've just discussed today, and we can discuss further in the discussion session. I'd like to thank the GLOW organizers again for inviting me. I hope you've enjoyed the talk, and let's dive into discussions. Thank you so much.
Thank you so much, Petar. Very, very interesting, and I'm sure we're gonna also have a lot of questions afterwards.